Today I'll be presenting Offload Annotations, a new approach for heterogeneous computing in existing libraries and workloads. I'm Gina, and this is joint work with my colleagues at Stanford, Shoumik and Deepak, and my advisor, Matei Zaharia. The cloud has recently made specialized hardware like GPUs cheaper and easier to use. What used to be thousands of dollars to buy for yourself now costs a few dollars per hour to rent on the cloud. As a result, people who've never used this technology before are looking for new ways to speed up their applications using hardware. For some background on how GPUs might be used to speed up your application, let's compare them to CPUs. CPUs are the most common processor found on our personal computers. While a typical CPU might be able to parallelize tasks 4 ways, a GPU has effectively thousands of cores that can concurrently execute many simpler tasks. For example, matrix addition is particularly fast on the GPU. However, there's also disadvantages to using the GPU. In general, GPUs have less memory than their CPU counterparts and crash if they run out of memory. In addition, if you want to use both processors in the same workload, like if only part of the task can be parallelized, you have to transfer your data to ensure that it's on the same device as the function that's using the data. The time it takes to move data around is proportional to its size and can be a costly bottleneck in heterogeneous applications that use both processors. With the trade-offs of CPUs and GPUs in mind, let's talk about data science, an application that started out using the CPU. Data science is done almost entirely in Python, a scripting language that's easy to write. The result is an ecosystem of popular Python libraries for doing data science on the CPU. Even if you don't do data science, you're probably familiar with these libraries, like NumPy, Pandas, and Scikit-Learn. Data science often involves analyzing large amounts of data, which makes it a natural fit for the GPU. Now that GPUs are cheaper, data scientists are looking for ways to bring heterogeneous computing to their existing workloads. The result is a similar ecosystem of Python libraries before the GPU. These Python libraries are very similar to their CPU library counterparts, claiming to mirror the APIs of the libraries that we saw earlier. The idea is, for example, once a data scientist knows how to use NumPy on the CPU, they can just as easily learn how to use PyTorch on the GPU because they share the same API. In fact, the online documentation for these GPU libraries all take great pride in their similarities to their CPU library counterparts. For example, cuDF provides a pandas-like API. CuPy's interface is highly compatible with NumPy and can be used as a drop-in replacement. PyTorch is a replacement for NumPy, and cuML's Python API matches the API from Scikit-Learn. These new GPU libraries all seem to promise a very seamless integration experience for using the GPU. But are they really as easy to use as they seem? Consider porting this machine learning workload to the GPU. In this workload, we pre-process the input data xtrain and train the model. Then we test the model on a different dataset xtest. At the end, we plot the results. Recall from the previous slide that cuML's Python API matches the API from Scikit-Learn, so we try to use cuML as a drop-in replacement for the CPU library, Scikit-Learn. We look for functions in the cuML documentation that correspond to the library functions in Scikit-Learn, and then we replace them in our code. We find that some, like standard scalar, don't exist at all, so we leave the original version. Remember that when using both processors, data has to be on the same device as the function that's using it. Since the inputs to the program xtrain, ytrain, and xtest are usually read from another step in the pipeline, we assume they start out on the CPU. Since standard scalar is on the CPU, but PCA is not, we transfer the outputs of standard scalar to the GPU. And then finally, since our plotting library requires the data to be on the CPU, we transfer the results back at the end of the program. Now we run the program, but then it crashes in the predict phase due to insufficient GPU memory. Remember from earlier that GPUs have less memory than their CPU counterparts. Since prediction can be done independently on different batches of data, we manually split the X-test data into batches that fit in GPU memory, and then independently execute the prediction phase for each batch. Thus, by paging the data, only a small amount of data is in the GPU at any time. Finally, the program runs to completion, but its performance is not much better than before the code became so complex. We think a different combination of CPU and GPU functions might make the program run faster, but since we manually inserted all those data transfer statements and replaced those functions ourselves, trying different schedules would also require a lot of manual work. It turns out that GPU libraries are not that easy to use after all. Our solution is Offload Annotations. With Offload Annotations, or OAs, we enable heterogeneous GPU computing in existing workloads with little to no code modifications. Our design involves three parties: an annotator, an end user, and a runtime. We'll discuss the role of each party in the design. Our goals for Offload Annotations are derived from our motivating example. With less developer effort, we'd like to at least match the performance of handwritten implementations using GPU libraries as a drop-in replacement. We'd like to automatically split and page data to scale to data sizes that normally cause the GPU to run out of memory. And we'd like to beat the performance of the original workload written for the CPU. Step 1, the annotator. Instead of making intrusive changes to the original workload or the original CPU library, we use a technique called annotations. The annotator takes advantage of the mirroring APIs between corresponding CPU and GPU libraries to write these non-intrusive offload annotations. In this case, the annotator picks two libraries, the CPU library NumPy, and annotates them with the GPU library PyTorch. After identifying the libraries, the annotator then identifies corresponding functions and uses the OA notation to link the two functions. Even though the two libraries claim to have similar APIs, their function names can still differ, like torch.mul and numpy.multiply. The annotator also needs to include the types of the inputs and the outputs in each function annotation. To do this, the annotator uses a special type called the offload split type, which is a wrapper around an actual type, in this case, NumPy's ND array. The offload split type allows the scheduler to dynamically infer information about the inputs and outputs at runtime. The annotator can also annotate allocation functions. Allocation annotations are later used by the runtime to optimize data transfers, since data transfers can take a lot of time. Note that allocation functions only have a return type. With the function annotations in place, what exactly is in an offload split type? Offload split types convey information to the runtime through an interface that the annotator implements for each type. The interface consists of 5 function calls. The first 2 function calls are part of the offloading API. The device function specifies which device the value is on, the CPU or the GPU, and the to function transfers the value from one device to another. The offloading API is used to automatically transfer data, which we had to do manually in the motivating example. To make the interface for offload split types concrete, we'll look at an implementation of ND array type for the API. In this case, device checks the type of the object, whether it's a torch tensor or a NumPy ND array, and 2 uses the transfer API from the PyTorch library to move data around. The next 3 function calls in the interface are part of the splitting API. The splitting API returns the number of elements that a value can be split in, and then describes how to correctly split data into data parallel chunks, and then how to merge them back together. The splitting API is the same as the one in the split annotations or Mozart paper from SOSP. Mozart uses the splitting API for cache pipelining on the CPU, while we use splitting for the totally new use case of automatically paging datasets into GPU memory. This is what we had to do manually in the motivating example. Since NumPy's ND array is a matrix, the splitting API for the ND array type is essentially matrix operations over the value. Overall, the offload split type interface can be easily generalized. We were able to implement the interface for other common types like Pandas data frames and machine learning models in Scikit-Learn. Step 2, the end user. The end user is the person who's actually responsible for writing application code and porting it to the GPU. In this case, the application is a simple Python program that uses many of the functions we previously annotated. Note that the end user doesn't have to be the same person as the annotator. In fact, we imagine an ecosystem similar to TypeScript in which a small number of annotators write these annotation files that can be shared amongst a large number of end users. To use the annotated library, the end user simply changes the import to import the annotated library instead. Now, the program, instead of calling actual function, calls our annotated wrappers to these functions. Since the annotated library calls a wrapper that feeds into our runtime, the runtime doesn't actually evaluate any values until it's required to. Thus, if the end user needs to materialize a value, say to use in a plotting library, they have to explicitly call the evaluate function to invoke the runtime. Step 3, the runtime. So each time the program calls an annotated function, the runtime adds a node to this lazy computation graph. The graph on this slide corresponds to our Python program from earlier. So in the graph, nodes represent a function call, and dotted lines represent an allocation function. The edges in the graph represent data dependencies. When evaluate is called, the runtime does a topological sort of the graph and produces a list of instructions that satisfy data dependencies. Next, Bach assigns each function to either the CPU or the GPU based on a naive scheduling algorithm. The algorithm is, if the function has a function annotation with a GPU library implementation, then Bach will assign the function to the GPU. Otherwise, it assigns it to the CPU. In this case, since we didn't annotate the arcsign function earlier with the GPU function, it gets assigned to the CPU. However, since multiply and square root do have function annotations, they get assigned to the GPU. Our scheduling algorithm is not meant to be optimal and definitely has room for improvement, but it was sufficient for our workloads. Next, the runtime assigns allocation functions to either the CPU or the GPU. The algorithm for this is to look at the first node in the graph that uses the allocated data and to assign the allocation to the same device as that node. For example, when assigning node 3, it looks at the function node 4. Since node 4 executes on the GPU, node 3 is also assigned to the GPU. Consider if we'd instead assign node 3 to the CPU. Then we'd have to first transfer the data from node 3 to the GPU before we can execute node 4. And since data transfers can take a lot of time, we like to avoid them when possible. Now that all functions and allocations have been assigned to a device, Bach uses the offloading API from earlier to automatically manage data transfers. So when looking at node 4, Bach will use the device API to figure out that the inputs from node 2 are located on the CPU. Then Bach will use the to API to transfer those inputs to the GPU. If the splitting API is implemented, Bach will use the size API to estimate the size of the working dataset. It'll compare it to the size of GPU memory. If it's larger than GPU memory, Bach will use the split API to split the data into a manageable chunk. Then at the end of execution, it'll use the merge API to merge the values back together. Altogether, by leveraging the offloading and splitting APIs implemented by the annotator, the Bach runtime can automatically manage data transfers and scheduling in a heterogeneous environment. To improve on the naive scheduling algorithm, we introduced a way for the scheduler to make slightly more informed decisions based on some heuristics. So say the runtime is trying to assign node 4 to a device. It'll do a cost-benefit analysis of either executing the function directly on the CPU or transferring its inputs derived from node 2 to the GPU and then doing the computation on the GPU. At large data sizes, it might be totally worth it to transfer the data to the GPU first, since computing on the GPU is so much faster. On the other hand, when the data size is small, it might be faster to just do the computation on the CPU and avoid the overheads of transferring data to the GPU. So using the heuristics, the runtime would assign node 4 to the CPU. So what do these heuristics look like in the code? The heuristics are actually Python functions provided by the annotator in the function annotations. The heuristics are functions of runtime data, like the offload split types of the inputs or the inputs themselves. The naive estimators here are functions of the input data size. Below a certain data size, the heuristic favors the CPU, and above it, it favors the GPU. Like the rest of scheduling, the algorithm here is rather naive. The heuristics particularly are more a proof of concept that the runtime captures a lot of information that can be automatically leveraged to make more informed scheduling decisions in the future. How did offload annotations perform in practice? We wrote offload annotations for 4 different GPU libraries and found that on average, a single library integration took 130 lines of code. The actual implementation for each integration looks very similar to what we described in the design. We evaluated Bach on 8 different workloads from library tutorials, Jupyter notebooks, and blog posts that we found online. Across all the workloads, we observed a maximum speedup of 1200x and a median speedup of 6.3x. We evaluated each workload on 3 different implementations. The CPU library implementation indicates the original workload before making any changes to port it to the GPU. The GPU library implementation indicates a handwritten implementation that uses a GPU library as a drop-in replacement. Finally, the Bach implementation indicates that we imported an annotated library into the code. On the x-axis, we vary the input size, and on the y-axis, we measure end-to-end runtime. Both these axes are on a logarithmic scale. And note that due to the logarithmic scale on the y-axis, the differences in runtime may be more or less than they actually seem. The dotted line indicates where the GPU implementation runs out of memory. And in this graph in the GPU library, the runtime is proportional to the data size until it runs out of memory and then crashes. We'll look at the 3 main takeaways of the results with this particular workload. Then we'll analyze 3 other workloads in more detail and then take a holistic look at all 8 workloads before concluding. The first takeaway is that without manually replacing functions in your code and writing data transfer statements, Bach can match the performance of handwritten GPU implementations. So in the graph, at the same data sizes, the 2 implementations have very similar runtimes. The second takeaway is that without manually splitting and paging data in your code, Bach can automatically scale to data sizes beyond where the GPU library runs out of memory. In the graph, Bach extends beyond the dotted line with no additional end-user effort. And finally, Bach consistently beats the performance of the CPU library implementation. Note that due to the log scale, the difference in runtime represents a constant multiplicative speedup. Now we'll take a look at 3 other workloads in more detail. In this workload, we look at the effects of allocating data directly on the device that first uses the data. By doing so, Bach is able to eliminate the initial data transfer in this workload and enable 4.6x speedups. However, When the data is too large to fit on the GPU, Bach is unable to allocate all the data on the GPU at once, because it'll run out of memory. Instead, it allocates the data on the CPU and then pages it into memory, adding an additional data transfer beyond this data size, thus reducing the speedup to 1.1x. Next, we evaluate heuristics. In this workload, we use the same linear estimators as described in the design, and thus smaller data sizes assign all computation to the CPU, while larger data sizes default to scheduling as many operations as possible on the GPU. As a result, the Bach runtime here is a minimum of the runtimes of the two other implementations. However, the heuristics aren't entirely necessary since the absolute runtimes at small data sizes are also so small. And finally, we evaluate splitting and paging large data sets into memory using the splitting API. This workload is the same as the one in the motivating example, where we first fit a model to some training data and then predict it on testing data. Before the GPU runs out of memory here, the Bach runtime is dominated by the time it takes to fit the model. As the data size increases, and because Bach is able to automatically page the dataset even when it no longer fits in memory, the absolute runtime advantage also becomes more significant, enabling speedups of 6.2x. In this workload, we don't really see the advantage of using the GPU except until Bach is able to page the datasets into memory. We evaluated 8 workloads in total, and we discussed the details in the paper. And since we've been looking at everything in a log-log scale, here's a brief look at what the data looks like when the y-axis is a linear scale. This version further emphasizes that the real advantage of Bach is at large data sizes, where the runtime differences are larger, and because Bach enables the workloads to scale automatically by splitting and paging large data sets. In conclusion, offload annotations enable heterogeneous computing in existing libraries and workloads with little to no code modifications. Our 3 main takeaways are that with less developer effort, Bach and offload annotations can match the performance of handwritten GPU implementations, scale to data sizes larger than GPU memory, and beat CPU performance. Our code is open source if you'd like to try offload annotations for yourself. Thank you for listening.